All right, welcome. Today we're jumping into one of the coolest parts of machine learning, clustering. This is all about how you discover the hidden structure, the natural patterns inside your data, especially when you don't have any labels to guide you. So yeah, let's get right into it. So imagine this. Somebody hands you a massive data set. It could be anything, customer behavior, network traffic, patient symptoms. But here's the catch. There's no answer column. Nobody's told you what the groups are supposed to be. Your job is just find the patterns. Where do you even start? Well, that is the exact problem that clustering is built to solve.
At its core, clustering is really just about finding the natural clumps in your data. Think about it like this. If you could plot every single data point in some huge, multidimensional space, clustering algorithms are what you'd use to find the dense spots, the areas where points are all huddled together, and draw circles around them. You're not trying to predict a label somebody else gave you. You're discovering the structure that was already there.
Now, this is a really important point. People often mix up clustering with classification, but honestly, they're two totally different beasts. Let's break down exactly why.
Okay, so here's the main difference. With classification, you start with the answers. Someone has already gone through and defined all the groups, things like fraudulent or not fraudulent. Your job is to train a model to predict those existing labels. We call that supervised learning. But clustering, that's unsupervised learning. You've got no labels, no predefined groups. You're just asking the algorithm, hey, are there any meaningful groups in here at all based only on the shape of the data itself? And this, right here, is what makes clustering so tricky, but also so cool. If you're doing classification, it's easy to see how well you did. You just check your model's predictions against the real labels. Simple. But with clustering, there's no ground truth. There's no answer key. So how on earth do you know if you found a good set of clusters? It's kind of like grading an essay test with no rubric. And that brings us to the most important point of all. The goal here isn't to find the one single true way the world is divided up. The goal is to find a set of groups that's useful for whatever you're trying to do. A 4-cluster model might be perfect for a marketing team, but a product team might need a 7-cluster model for more detail. At the end of the day, usefulness is the only thing that matters.
Okay, so we get it. We want to find clumps. How do we actually do it? Well, there are a ton of different algorithms out there, but they mostly fall into a few big families, each with its own way of thinking. Let's go on a quick tour.
All right, first up is the most famous one, k-means. It's actually beautifully simple. You start by telling it how many clusters you want. We'll call that number k. So let's say k is 3. The algorithm drops 3 random center points called centroids into your data. Then it just does this little 2-step dance over and over. First, it assigns every data point to whichever centroid is closest. Then second, it moves each centroid to the average spot of all the points that were just assigned to it. You just keep repeating that assign and update loop until the groups stop changing. That's it.
Now for something totally different. DBSCAN. Instead of trying to carve up all the data, DBSCAN thinks about clusters as just dense areas of points. And what's so cool about this is that any point that's not in a dense area gets labeled as noise. This makes DBSCAN amazing at finding outliers automatically. And it can find clusters that have really weird shapes, like crescents or squiggles, that would totally confuse an algorithm like k-means. This little table really sums up the trade-offs. You've got k-means, which we said is super fast, but kind of assumes your clusters are nice, round blobs. And we just talked about DBSCAN, which is the champion for weird shapes and spotting outliers. Then you have things like hierarchical clustering, which doesn't give you one answer, but builds a whole tree of possibilities, which is awesome for exploring. And finally, GMMs, or Gaussian Mixture Models, which are more flexible and can handle more elliptical or oval-shaped clusters. So this brings us to the million-dollar question, right? For an algorithm like k-means, how in the world do you pick the right number of clusters? How do you choose k? You don't know ahead of time if you have 3 customer types or 10. Let's look at how you figure that out. So there are a couple of common statistical tools to guide you. The first is called the elbow method. You basically try a bunch of different k values, say from 2 to 15, and for each one you plot how tightly packed the clusters are. You're looking for the elbow in that graph. The point where adding another cluster doesn't really make things much better. Then there's the silhouette score. This one's a little different. It basically measures, for each point, how well it fits in its own cluster compared to the next closest one. You just pick the k with the highest average score. But, and this is the real secret, the math might tell you that k equals 8 is the absolute best fit for the data. But if your sales team can only handle, say, 3 or 4 different types of customer outreach strategies, then 8 is just not a useful number. A slightly less perfect model that people can actually understand and act on is always better than a statistically perfect one that nobody uses.
And that brings me to what I think is the most important test of all, and it's not a number. It's this. Can you look at the items in each cluster and tell a story about them? If you can confidently give your groups names, like power users, weekend shoppers, and bargain hunters, that's a fantastic sign you found something real. But if a cluster just looks like a random mess of unrelated things, it's probably not a useful group.
And please, remember this. Sometimes the most honest and correct answer is that there are no clear groups. Your data might just be one big, smooth spectrum. And saying that, concluding that no real segmentation exists, isn't a failure. It's actually a hugely valuable finding. It stops your team from chasing ghosts and making bad decisions based on lines that aren't really there.
Okay, so we know what clustering is and how to do it, but where does the rubber meet the road? Where do we actually use this stuff? Well, the applications are pretty much everywhere. So yeah, customer segmentation is the classic example, but that's just scratching the surface. Recommendation engines like on Netflix or Spotify cluster people with similar tastes to suggest what you might like next. Cybersecurity systems use it to find weird patterns in network traffic that could signal an attack. And get this, in medicine, clustering patient data has helped scientists discover completely new subtypes of diseases like cancer, which helps create better, more targeted treatments. It's everywhere.
So if you only take one thing away from our chat today, let it be this. Clustering is not an answer machine. It's a discovery engine. It's a way to explore your data, to generate new ideas, and to start asking smarter questions that you probably didn't even know you should be asking in the first place. And that's really what makes this so powerful. It gives you a new lens to look at your data and see what might be hiding there in plain sight. So I'll leave you with this question. What hidden structures, what undiscovered groups are just sitting there, waiting to be found in your data?